go through some of the questions. I hate these answers. They stack the heck out of me. Go away. Right. So hopefully you are looking at the homework for 12A. Is that what you're saying? Okay. So pretty much going to do these questions together. They're good. So they give you a kind of idea and the beginnings of hypothesis testing. So an example hypothesized that the proportion of babies born during the full moon should be 1/29.53, and they got that because that's essentially how many, what fraction of the month is a full moon. Right? Full moon's about 29, 30 days on average. If babies are born during this full moon, that's one of the days. So you'd expect if there was nothing, if the full moon had nothing to do with babies being born, then the answer would be 1/29.53. And in this story, they go and ask you, what is the population of interest? And if we read through it, we find out it's all about babies. And it says, specify the population parameter. And the population parameter is the proportion of babies born during the full moon. And it says, write down what the null hypothesis would be, and it would be P equals 1 divided by 29.53. So that's not a full hypothesis test, but it's the beginning of one, right? Now, if it was a full one, maybe some scientists would say, I think it's higher than that. I think babies get born more often during a full moon than that number, right? That would be the number if it wasn't anything special. And I think it was more. And if they did have a more, wouldn't there be an HA right next to the H naught? And HA would say P is bigger than whatever that decimal is. And here's our second story. Professional tennis player Martina Navratilova, Monica Seles, Rafael Nadal, John McEnroe, and Jimmy Connors, all very famous people, if you're into tennis, and they're all left-handed. Define the parameter P for the proportion of professional tennis players, current and retired, are left-handed. So, and researchers are interested in testing the hypothesis that good tennis players, it's more than 10%. Okay. So what is the population, right? We're looking at population here, and it's one of these 5 guys. I've got my answer here. And it's that one. Right. We're not interested in people in the entire world. Isn't this to do with tennis players and left-handed in particular, but tennis players in general, and retired and being professional, or not retired and being professional, right? And then one of these sentences here is going to be the one that basically describes this thing. And researchers are interested in the hypothesis that the proportion of current and retired is greater than 0.1. So that's what it would look like in English. So what they might do in that story is, couldn't you collect data on all professional football players over the last 20 years? And hopefully, you know if they're left or right-handed. And you can find out what that proportion is. And if it's bigger than 10%, you might have evidence to prove what you're after. Now, if you can't get everybody, which is probably true, can you do a random sample of 100 professional tennis players?
Professor Robertson, I got an email that Lake is in the waiting room.
Gotcha. There she is. She's in. So in this case here, you would go and you test it out and see if it come out true.
I actually want to know the answer to that. I think it makes sense to me.
That left-handed players are more likely to be higher in that population than just the normal amount of left-handed?
Yeah, I think just because playing tennis, you have to be kind of ambidextrous. You know, you're wherever the ball lands, you have to be able to hit with your left hand or your right hand. And if you're a left-handed person in a right-handed world, your right hand is gonna probably be more dominant than a right-handed person in a right-handed world who isn't using their left hand as much. It just kind of makes sense that someone who's
Yeah,
already
it does. It does. I have seen. If you are fighting, boxers are fighting. Do you know a southpaw, a left-handed boxer, tends to be more successful because left-handed boxers are forever fighting right-handed people, so they're quite adept at doing that. But right-handed people don't get to fight as many left-handed people, and so they're at a disadvantage. So yeah, left-handed boxers are better than right-handed boxers in the sense they're more successful.
Yeah, and I guess then there shouldn't be more left-handed tennis players. They'll just be better left-handed tennis players.
Well, I don't know. Maybe not. It'd be an interesting answer. I wish the government would give me some money and I'd go and do it. Or give you money, David. And, well, we've done that one. Okay, move on to question 3. Keep all my answers handy. State a null and alternate hypothesis. Now, right now, they're doing it in English, right? That'll turn into P is 0.5 and P is less than 0.5 later. But right now, it's in English. So here is the story. Will an increase in speed limits on interstate highways lead to an increase in highway fatalities? So, in English, one of these 5 would be your null and your alternate. And I'm looking at this one as answer. Is it that one I picked? No, I picked this one. Yeah. Increasing speed limits on interstate highways does not increase the fatality rate. The null hypothesis is nothing's happening here. That's always the null hypothesis. So that would be, it's still 20% or whatever the accident rate truly is. It's still 0.1%, right? And the alternate is the one that matters, right? So that would be it. In this case, would that be a, well, they call it one-sided and two-sided. I would probably change that name a little bit. When you are looking for an increase, aren't you saying that P is actually bigger than nothing happening? And so it is a one-sided, but I would call it a right-sided, because if P is bigger than a number, it's right-sided test. If P is less than, it's a left-sided test. Left-tailed, and if it's not the same, right, you pick 2 sides. Okay, when a coin is spun on its edge, the probability that it will land heads up is equal to 0.5. Okay, I had a lot of trouble with this one, so I just looked up their answer, and they said it was this one. The probability is 0.5 that it's spun on its edge and it lands heads up. Oh, okay. They just said it's 0.5 or it's something different. So that's a two-sided one. Okay, makes sense now. Okay, question 4. Suppose that the present rate of success in a treatment of a particular psychiatric disorder is known to be 58%, right? 0.58. A research group hopes to demonstrate that the success rate of a new treatment is better than that. So we want to set up the null and alternate hypothesis based on this story. So it's always equal. H naught is always P equals something. And in this case, it's going to be 0.58. And they are looking to demonstrate, to prove that it's better. So in this case, better means bigger, right? More successful than 0.58. Now that makes sense. So that would be like the first step in a hypothesis test, right? To put an H naught and an HA and put numbers to them. Suppose that a statistics teacher asks his students to each randomly pick a number from 0 to 8. His general theory is that the proportion who pick the number 0 would be less than that you'd expect if it was random. So what specific value of P would you expect if you just randomly chose a digit? What percentage should be a 0? Not even a percentage, what proportion would be a 0? Would you agree 185? Right, there's 1, 2, 3, 5 numbers. If you just randomly picked a number, the probability that you chose 0 should be 185. If you want, we'll call it 0.2. So the null hypothesis is going to be P equals 0.2. What do you think a not equals? I just told you the answer. What would you expect if it wasn't random, right? Well, if it was not random, you'd expect it not to be that number, right? It could be more, it could be less. And I've just get distracted by this exclamation mark equals. That didn't work. Maybe you do exclamation mark. Where are you hiding exclamation mark? I saw you a second ago. Exclamation mark. Okay, that's not working. What the heck are they talking about here? I guess, do you just type that in?
Yeah, I don't know if they're thinking that it will change. I think that they just read that as doesn't equal.
Okay, so, okay. I wonder why you can't just find it over here. Let's see if it's hiding. Oh, come on. Couldn't they just put a little guy there with the not equal sign and you just hit it? Oh, come on, WebAssign. I mean, if you knew that was a problem, shouldn't you have went over here and fixed your programming a little bit? Okay, it looks weird, but that's what not equals looks like. So I guess now we know if we ever have to put not equals, it's exclamation mark equals. I think three more questions. Confidence intervals and hypothesis tests are two major categories of statistical inference. That's how we decide is there statistical significance, right? On the basis of this information, do you think a null and alternate hypothesis are generally statements about a population, about a sample, or both? When we say the null hypothesis P equals 0.5 and the alternate P is not equal to 0.5, when we do that, are we talking about the population parameter, the sample parameter, or both? That's the question. So which of those three is it? We are talking about which one of these three?
Populations.
Yay, correct. Okay, you can read this really cool story, but we don't have time. Well, that may interest you, David. An anthropologist is trying to determine if people in a certain region are descended from the same ancestors as those in another region. She knows that the region she studied, 11% of the population have a particular genetic trait, right? So we got a lot of information now that we didn't have 50 years ago, right? The DNA, where you can actually localize parts of the DNA and come up with genetic traits. And she plans to take a random sample of people from the new region to test them for that trait. If the population of the population with this trait in the new region differs from hers, then that's her proof that they're not the same ancestry, right? So if they're not the same kind of number, she's going to kick it out. So if you look through this entire list, let's see what this one looks like. It's question 7. Have a look at my answers. Okay. H note, in the U region being studied, 11% of the population has a unique trait. In the new region being studied, the percentage of unique genetic traits differs from 11. So we're doing it's 11 or it's not 11. So that would be P equals 11. And this would P not equal to 11. Paul, I won't do this one. You can do that one. And yeah, you can do that one. Okay. So what we've kind of done here is just went through that first section. I just wanted to get that kind of out of the way so that we can get into the meat, the good stuff. So here are some terms that are used in hypothesis tests. We've seen some of them. Population, right? What's the population of interest? Population parameter, right? Like the one we just saw a minute ago, could be P equals 0.11, which means that the population number used to be 11%, or the other group, it was 11%. And then we have a null and alternate. And our null hypothesis tends to be P equals something. Right, so it could be 11, it could be 50%, it could be 1 over 29.3. And then the alternate only takes 3 forms. The alternate hypothesis, when we write it down with numbers, only has 3 forms. We either believe that the real number is less than this, more than this, or just not the same as this. And when it's less than it, it's a left-sided test. When it's more than it, it's a right-sided test. And when it's not equal to it, right, it's a two-sided test. So these two guys here and here are one-sided tests. This one is left-sided, this is right-sided. And a not equal to, that would be called a two-sided test. And then we have a guy called the statistic parameter, or just p hat. Isn't that the guy that you get from your sample? So you believe that well, the null hypothesis is that it's 11%, and you go and you collect a sample, and you find out what it is in the sample. And it's bigger than 11 or less than 11, whatever. And that's called the statistic parameter. The significance level, it's 1%, it's 5%, it's 10%. We used that yesterday, and we're going to use it again today. Isn't that the guy that you compare your p-value to? And if it's less than that, you've got your evidence, and if it's not, you don't. And I believe today I got it the right way around. The z-score, p hat, the sample statistic, take away p, which in this case would probably be 0.3, divided by this tiny little square root of pq over n, which is use that number there as your p, your q, and n comes from your sample. And then you get a guy called the p-value. And the p-value is the probability that this z-score is bigger than a number that you got or less than the number, right? So whatever the z-score is equal to is the probability that z is bigger than your z-score or it is less than your z-score. And we put that whole package together. When we're finished, we should be able to say there is evidence to prove that that new psychiatric test is better, right? More successful. Or there's evidence to prove that this other tribe is different from the first tribe, right? Not equal to would mean it was different. that was the guys we used yesterday. This is just some more detail based on that. So I'm going to go now, and hopefully I've got another question to talk about. Click on it. Open up. And here we go. Right, so this here is going to, basically we're going to do some skill building. So we're going to get practice at finding p-values. So suppose you know or are told that the null hypothesis is that guy, and that the alternate hypothesis is, I don't know, say bigger than 0.1. And the Z statistic, and you are told that it is 2.2. We are going to find the p-value. Now that's the probability that you get a Z score less than 2.2, more than 2.2. Which one of them is it going to be? Well, you decide that by looking up here. Do you see how this is greater than 0.1? So you're looking for what's the chance that you get a Z score greater than 2.2. So if you're wondering which way around to do your p-value, is it greater than the number or less than the number? It has the same direction as this other. Right, at this point, we go and we use salt, because salt is going to tell us the probability that you get a Z score greater than 2.2. So I'm now going to move over to the screen, and with a bit of luck, you'll be looking at one of those questions. Here's a whole load of them. I'm just going to plug this in, bring this along. Can you see salt now? Can you see statistic? Okay, it's too big. I'm going to have to shrink it a little bit. There. Now, the one that I've got that you can't see anymore is Z greater than 2.2, right? Is that right-tailed, left-tailed, or both-tailed? Which one of these circles here do I pick? Right-tailed, left-tailed, both-tailed. Which one do I pick?
Right-tailed.
Agreed. Can you see it's that number or bigger visually? Now, over here, keep that as 0 and 1. That's never going to change. Take this guy and write down the number that we had, which is 2.2. And the p-value is this guy underneath. So the p-value in this case is 0.0139. Are you happy about how we got that guy? Okay, we're good. Now, I'm going to be bouncing back between some screens here. That was an example of what's called a right-tailed test. Suppose the question had p equals 0.1. The alternate was p not equal to 0.1. And the Z statistic was 2.2. How do we get the p-value in this case? Well, we know it's the probability. Technically, oops, I'm trying to figure out a best way of saying this. Basically, we want a two-tailed test. Let's do it visually. So we're looking at the chances that it's not this bit in the middle. So it's bigger than 2.2. at least in this situation. So let's show you how you do that using salt. And it's going to look very similar to what I just did. So are you hopefully looking at the salt? Now, this one was a not equal to, wasn't it? I know that this Z score was big, so that's why I went right-handed and got a bit confused with myself. But I'm going to put in both because it's a two-tailed test. Whenever it's a not equals to, it's a two-tailed test. And I go in here and I put in the number 2.2. And I put in the number 2.2. So do you see a two-tailed test is not just one side? It could have ended up being the other side. So we have to count both situations. Even although the Z score I got was only the positive number, when it's a two-tailed test, you assume that it might have been the negative one as well. So it's a plus 2.2 and a negative 2.2. And when I do that, can you see that the answer that we get for this one is a p-value of 0.02781. The p-value is this guy here. So a left-tailed and a right-tailed are pretty easy. The two-tailed, you have to be a little bit more careful, right? If it's a not equal to story, that's what a two-tailed looks like. Make sure you hit both tails and make sure whatever the Z score is, whether it's positive or negative, doesn't matter. Because if you are told the Z score is positive, then fill in the negative on this side. Maybe the next time the Z score is negative, remember to fill in the positive one on the other side. It's a two-tailed, it's a two-sided thing, right? It's a two-tailed situation. Are we good with that? How to use salt to get a p-value. So let me pick a different one in this list here then. This guy here is 4.24. The null is 0.25 and the alternate is it's bigger. Isn't this a right tail test then? So when I hit salt, I'm going to just remember the 4.25 part and that it's right tailed. So I hit salt. I remember it's right tailed. And I wish I could remember what the number was. I think it was 4.25. Let's pretend it was. And the answer I get is a whole load of zeros. Can you see that the chances you get a Z score of 4.25 by sheer randomness is almost impossible? It's a very, very small number. That's the evidence that you would eventually get to prove that the alternate was correct. Let's be silly and put in a Z score of 7. That actually annoys salt because isn't the answer 0? And it tries to tell you that it doesn't like 0. It's not really 0. It's 0.24 zeros in a 3 or something, but it can only fit in so many digits, so it rounds it off, right? But a 0 p-value is a miraculous thing. You will very rarely get them in real life experiments, although occasionally you get lucky and you do. Okay, are we cool about how to get p-values? Do you need to see another example of that, or can we move on to the next phase? You want to see more or not? I kind of need feedback. No? Okay, that'll work. So, can you see question 2 here? Okay, so a hypothesis test is done to determine if the proportion of a certain ethnic group having blood type A is greater than 30%. Okay, null hypothesis. Oh, do you see this guy P naught, who he is? that's just the number that would go in your H naught. Do you know how you say H naught P equals 0.30? They very often call that number P naught, if you're wondering. So that's what that was. The sample statistic in this case, right, was 0.0029. And we should be getting a p-value out of that. So I'm going to have to write all this stuff down now. So here we go. This person is wanting to see if the proportion of people in a particular ethnic group with blood type A is greater than 30%. Greater than 30%, or it's equal to 30%. That guy there, that number there, is called P naught. I don't think they use it much, but if they do, that's where it comes from. Now, they told me the Z-score, which was really nice of them. And they told me it was 2.76. And they are asking me to find the p-value. Now, the p-value is the probability that you get a Z-score bigger or less than that number. Well, looking at my story, bigger or less than 2.76. Which should it be?
Bigger.
Great. Remember what I said, that whatever this is doing, that's going to do the same direction, right? Now, at this point, you go and you do the p-value. So I'm clicking on that, even if you can't see it. And let's do a p-value then. Wouldn't it be really cool if I had 3 screens? I'd have one over here and one over here. Right. We are looking for the probability that Z is greater than 2.76. Greater than is a right tail test. Greater than 2.76. It's a one-tailed test. So there's your answer. The p-value is 0.0028. And that's you finished with that question. Now, I wish they'd done the whole analysis. I think that would have been, it's a waste of a good question. You know, where we go all the way from start to finish. But you get what you get. So let's get practice at finding Z-scores. So I have a hypothesis that says P is 0.7, and I have an alternate hypothesis that P is actually, well, let's do a less than 0.7. And in this data, we collect a random sample of 200 people. And we find out that in this particular random sample, P hat ends up being 0.65. And we are just going to find the Z-score, right? The Z statistic. And I'll do that in a minute. But since I've got this stuff here, left-tailed, right-tailed, two-tailed. What kind of test is this? Right, left, or two?
Left.
Agreed. Now, won't that be helpful when we do salt and we have to pick left tail, right tail, two tails? Remember that? Now, in this case, P hat, take away P over the square root of PQ over N. That's the Z score. P hat is 0.65. P, that guy there, is 0.7. And this fella uses that one. So it's a 0.7 times a Q, which is 0.3, and it's going to be divided by 200. So when you're doing this calculation, will you remember to use this guy up here and not this fella, right? So use 0.7, not this guy. I'm going to be brave here because I think this one I can just about do on the calculator in one go. So a bracket, 0.65, take away 0.7, close the bracket, divided by a square root of 0.7 times 0.3 divided by 200. And close the bracket for safety. And I get a Z score of negative 1.5. And that's where you would stop in this question. There's more to do in the hypothesis test, but we are only going to go as far right now as the Z scores. Are we comfortable about, if you get an information, how you would get a Z score? If I was going to go a little bit further, wouldn't the next step be to get the p-value? And the p-value would be the probability that I get a Z score less than negative 1.5. And then I would use salt here, wouldn't I? And I'd get an answer. And then I'd go a bit further and do my test, and then I'd go a bit further and get my conclusion. But right now, we're just stopping there. Let's do another one of these Z score guys. Okay, that'll be the last one for today. Right. H naught is the probability that someone picks a digit at random is 0.1. So you lot are going to give me some data here because I want to use it. Randomly think of a digit between 0 and 9. Right? You've all thought of a random digit between 0 and 9. And there's 5, 10, 15, 20. There's 22 of you. Okay, put your little thumbs up thing if you chose 0. Oh God, that's not the number I want. Right, Cheyenne doesn't know it, but she really picked 0 and then she changed her mind.
Are you going to cause an error by choosing too many zeros?
Probably, right. So, my alternate hypothesis is that P is not equal to 0.1. And I got a P hat of 1 out of 22. I just didn't want 0. So 1 divided by 22. And the answer I got here is 0.0455 if you round it off. Okay. Not that I couldn't have got 0. 0 would have been fine. It would have worked. But the only reason I'm doing this is to calculate a Z score. And the Z score is P hat, take away P over the standard deviation, which is that guy. So it's 0.0455, take away a 0.1, divided by the square root of a 0.1, 0.9, and divided by 22. So again, I'm going to try it in one go on the calculator. bracket 0.0455, take away 0.1, close the brackets, divided by, and then the square root stuff. And I get the answer negative 0.852. I can tell you right now that that is not going to be significant. Right? I could calculate the p-value. It'll be pretty big. I mean, it won't be 5 or 10, 20%, but it'll be pretty big. And the answer then to this hypothesis test is that there is no evidence to prove that people choose 0 less than what they randomly would anyway, or different at least than they randomly would. Right, now that's a not equals to, isn't it? If I was doing a salt thing to get a p-value, wouldn't that be a two-tailed? And although technically I'm doing a z-score, I'm doing a z-score less than a negative number. Really, when we do the thing, won't it be a negative on one side and the same number a positive on the other side, right? Because when you pick a two-tailed, you get both numbers, right? So you just got to remember when you do a two-tailed, I don't care what that number is, it's just whatever it is, make sure the other guy is on the other side, right? So if it's negative, make sure you put in the positive one. If it's positive, make sure you put in the negative one, and that will get you the correct p-value. Why do I know that that's not going to be significant? Just by looking at the number, I know it's not. You mentioned it yesterday. What kind of z-scores do you typically get most data in? It's always between 3 and negative 3, isn't it? So if you get a number in the middle, you know, a 0.1, a 0.8, it's really not that interesting. It's very typical. It's the kind of number you'd expect to get. Now, if that had been a z-score of negative 3.85 or positive 3.85, I bet you I would have got a statistically significant result, and I would have been able to prove. Now, I'm pretty sure, based on a very small sample, that the truth is that people don't pick zeros very often. The reason I couldn't detect it was my sample size was tiny. And when the sample size is tiny, it's very, very difficult to prove anything. And it's actually a bit dangerous to try and prove anything as well. Okay, you guys say hi and bye-bye.